exactly on it's exactly on the hour here. So welcome to the third presentation of finalists for the ADIA Lab JFDS Best Paper Award. We have 4 papers that have been selected by the readers of the Journal of Financial Data Sciences, JFDS, and they will give presentations now to a review panel that is virtually assembled. And with that, I would like to welcome Guillaume Chevalier, Guillaume Coqueret, and Thomas Raffinot. And Thomas is going to present their work about interpretable supervised portfolios. Please go ahead, Thomas.
Thank you very much. Just let me introduce myself. I have a master PhD, a master in statistics, a PhD in economics. I've worked as a macro strategist for 10 years, and then I went back to data science 10 years ago. I lead a team at AXA IM where called Quant Investment Signals within the multi-asset quant solution division, where our job is to data enhance the investment decision process, from data gathering, graph automating, to tactical indicator creation, tactical indicator based on machine learning, and portfolio construction. And in fact, this work is born from frustration, because I am a former economist. The lead PM was a former economist. He's working now at ADIA, by the way, Mathieu Loire. And our boss, who is the lead PM of the flagship, Laurent Clavel, was a former economist. And where we thought we had some value added is on creating features that link macroeconomic theory on a daily basis to market. And we were quite frustrated with the current framework for traditional framework for asset allocation. That where this work is born. In fact, it's a trilogy, but I will sum up the first 2 papers. The first one is called Supervised Portfolio. And the main idea is that we want to transform the optimization problem for asset allocation to a forecasting problem. In other words, we want to have a direct link between our features and the way we allocate capital. How we can do that? The traditional framework is in 2 steps. First, you create a forecasting model for expected return, and then based on expected returns and expected risk, variance, covariance, you put it into an optimization tool. It can be Markowitz, it can be a hierarchical approach, whatever. And then you have your weights, but you don't have any link between the features and the way you allocate capital. Our approach that we, in the first paper, is that we start by creating the optimization by starting with the optimization problem, knowing the future. So if we know what is the future returns, the future risk, and the future variance, what should have been the weight that we should have had at this time? So we create a perfect strategy, if I may say, and then we try to forecast this perfect strategy. So because yes, and now we have a direct link with between our features and the weights. In fact, it is really a traditional supervised machine learning problem. And what we show in the paper, that it leads to more stable portfolio, better risk-adjusted performances, and we show that nonlinearity matters. And for nonlinearities, we have used boosting model, and I'm not sure everyone is familiar with boosting model, so I will just introduce them very quickly, because we will use it in the second part, in the interpretable approach. So what is a boosting approach? Is very simple idea. It's an iterative process where the errors are kept being modeled. In fact, you start with the first model. With this first model, you have residuals, which is the blue line minus the green line, and you create a second model with that. We want to start with weak model, what we call weak learner, and then we create an ensemble model mixing all the trees in our case here. The main advantage is to be able to tackle non-linearity. In macroeconomy, the traditional way to describe non-linearity is the following one. The housing market weights, I don't know, 10% of the GDP. When there is a decrease in the housing market, it should have almost no impact, yet it creates recessions, because if you don't change house, you don't buy the new flat, the new pieces of furniture, and so on. So there is no consumption at all. So the big advantage for me of machine learning algorithms such as boosting is tackle non-linearity. Of course, there is no free lunch, though there is a lack of interpretability, many parameters to tune, and it's prone to overfitting. And the lack of interpretability was the main issue at AXA-IM, because we had some good models that told portfolio manager how they should allocate capital, but why should them trust us? So that's the second paper. It's all about interpretable ML. And why do we need interpretability? The main reason, I don't think it's in this jury, but people hate algorithm. That's what we call algorithm aversion. In fact, we forgive forecasting mistake made by human much more than those made by machines. We may say that's why economists still have a job. And the traditional example is the following one. Imagine you drive to your office in the morning and you run into the traffic. You forecast that a better road will be faster, and you take it. Later on, you learn that, in fact, you made a mistake. That's life, but it sucks, but that's life. In the same case, imagine that your GPS told you to change road, and it was a mistake. In this case, the probability that you will use your GPS again is quite low. In fact, that's really people hating algorithms and algorithm mistake. And in such high stakes, such as medicine, biology, and policymaking, you need interpretability. There is, in fact, two different branches for interpretability. The first one is post hoc methods, sorry. You start by creating your model, and then you try to explain it. There are global methods, such as feature permutation, to describe how feature affect the prediction on average, or local ones that are quite popular at the moment, such as Lime or Shapley values, where you try to explain individual prediction. And then you sum up and you have a global prediction if you want to. And the second approach, which is completely different, it's to create a model that is interpretable by nature. We look at both branches, and in fact, we find that there are many drawbacks to the post hoc approach. In the first paper that I quote here, is that post hoc explanations are very fragile. In fact, in this paper, the authors have almost the same explanatory variables. They get the same prediction, which is what we expect, but they were given two different interpretations. So which one is the right one? We don't know. And in fact, you can't really, it's not always reliable. In this paper by Slack and all, the author create a racist credit model. So in fact, if you are colored, you don't get a credit, and if you are not, you get it. But when they create the model, in fact, the color never appears as one of the main features. So they managed to tweak their own model to hide the most important variable. And lastly, even if you have explanation, in fact, here you have a classical paper by Ribeiro, so that's when they introduced Lime, where they show that they have created a model that is able to classify husky or wolf. So that was a good model. And when they look at it, they see that they have created a snow detector, because the only feature that matters if there is snow, it's a wolf. If there is not, it's a husky. So in fact, the main issue that your model is not. The good news is that you don't put this kind of model into production, so that's a good thing, and interpretability is always a good thing. But in this case, your model is still not trustworthy. So what we really wanted to achieve is trustworthy models. So we look at interpretable algorithms, those that are interpretable by nature, such as linear regressions, decision tree, rules. And the main issue with that is that they do not perform well. In fact, they are used as weak models in ensemble models. So if they are called weak, that's for a good reason. They do not perform quite well. And at the end, as portfolio manager, we are judged on the performances. If we can explain the way we allocate capital, it's a better thing. But if we don't manage to perform, we will be fired, for sure. So we discover that some authors in the statistic literature have tackled this issue by trying to take the best of both approaches. So interpretability and rules. There are methods such as rule fit by Friedman and Popescu. Friedman is one of the creators of boosting. And the one I like to use too is Cyrus by Bénard and al., which is based on random forest. And the idea is very simple. After the fact, when you discover the idea, you say, ah, yes, it's very clever, but I would have never had this kind of idea. So it's rule fit, it's just a linear regression with clever interaction. I will come back to that. So that's a two-step algorithm where you fit a sparse linear model with feature interaction. So the first one is to create trees, like from boosting models, where you will have an ensemble of models. And every path of a tree can be transformed into a decision rule by skipping the prediction and only keeping the, yes, when you separate the variables. I will take an example then. And then you take a global model. So you have all your decision rules derived from the decision tree. And you put that into a lasso, a sparse regression. So the traditional approach by Friedman and Popescu was a lasso. In the paper, I think that we use adaptive lasso, which has been created after 2000, or just at the moment that in 2006, sorry. Because it tackles some issue of the lasso for the OVAC propriety. In other words, it performs feature selection a little bit in a better way than lasso, but it's not a big deal. And let me give an example of how we can derive rules from trees that will be easier to understand. So let's imagine we have the full sample. The first cut is the first level rule if the market cap above 55 percentile. So yes, no. So we have large stocks and small stocks. Is the volatility quite high or no? And then the rule in our model will be market cap quite high and volatility high, market cap high, volatility low, market cap low, momentum quite low, and market cap quite low and momentum quite high. So we will have 4 new features. And in fact, it's really interactions that we used to do by hand that created by the machine. That's the main advantage of that. And at the end, you get a linear regression, so something that is quite easy to understand. If we give a toy example, in fact, we try to forecast the Boston, that's the Boston datasets where we try to forecast the median housing value based on different features. So what we can find here is that we have the beta, the traditional approach of the beta. The coverage, in fact, for rules is how often it is activated. All the math formula are in the paper. I really want to focus on IDs. That's why I try to go fast on math and really try to focus on IDs and results. So if you want the complete definition of importance and so on, everything is in the paper. And based on the beta, and you can create a feature importance. So here what we can see is that the main important feature is LStat, in fact, which is a feature to say if the neighborhood is poor or not. The chase is how far you are from the river. And then you have the first intersection. Is the neighborhood quite cheap? And if is the room RM, I think it's the number of room, quite high, and so on. So the main advantage is you mix a linear approach and non-linearity, and it's very easy to interpret. But as we can say, there are the big issues. We talk about performances. And what we wanted to check if, like rule fit is a simplification of boosting model, is it still performing quite well? So is there an interpretability performances trade-off, or can we tackle it with this approach? So we get back to a prediction model, a traditional approach by Gu and al, where we create a global model where we try to forecast, in our case, weights and not expected returns as a traditional approach. So we have 2 kind of labels: weights coming from the optimizer, weights, and weights minus the equality weight portfolio or the benchmark. The idea here is to make weights more homogeneous, more easy to learn for a model. So there is no linear approach because we know with the first paper that non-linearity matters. Then what we try to want is to create a backtest, but we want to tackle data snooping. The main idea of data snooping is that if we torture them, data are like men, if we torture them long enough, they will confess to everything. So we really want to take multiple testing, data snooping into account, and by that we use the model confidence set, which is in fact a generalization of the Diebold-Mariano test that can tackle multiple testing. In fact, there is an article by Diebold, which is called the Diebold the use and abuse of the Diebold-Mariano test, where he advocates to use the model confidence set. The main results of the model confidence set is like a set of p-value, like a ranking. In fact, we won't select the best model, but all the models that are equivalent from a statistical point of view. So we will have a ranking of p-values, and high p-values, which is high ranking, will be almost equivalent from a statistical point of view. So for the application, for the interpretability accuracy trade-off, we very simple approach, a constraint Markowitz with different investment universe, so that differ in homogeneity, so 10 industries, 25 portfolio, or as we are in a multi-asset division, multi-asset investment universe. Different type of predictors, very simple. So momentum and volatility, some macroeconomic series such as the yield curve, TEF spread, VIX, US credit spread, very simple. That's not what we are using in production at AXIM at the moment for sure, but that was what we decided to use in the paper. We take a traditional, yes, for the hyperparameters, we almost skipped the basic one. In fact, we could have skipped this one, and then we do a rolling regression, a rolling back test on a weekly basis. Models are updated on each semester. Yes, and we make sure that we have no data leakage, and we don't make when we create the investment strategy. We take 3 different investment horizons, 3 different level of risk aversion, different weights constraints. So we have many options, and what we wanted to look is this kind of graphs where we see the results of the MCS. So we really want only to look at MCS, and if rule fit and XGBoost are almost equivalent, here we can see that XGBoost seems to be a little bit better. Here we have almost rule fit that managed to be equivalent, even a little bit better than XGBoost. For the second approach, for the multi-asset portfolio, XGBoost seems to be better for sure, especially in the more homogeneous approach. But yet, rule fit model still manage to perform quite well in every situation. So we are losing some forecast accuracy for sure, but given the interpretability that we get, in fact, that's not what we could say that's a trade-off. We don't consider that's a trade-off. We consider that's a good approach when interpretability matters and performances matters. So when everything matters, go to rule fit. When only performance matters, go to XGBoost. That's what we find in this accuracy interpretability trade-off. And the second really application was to focus on stocks and stock characteristics. In fact, I liked a paper from Demiguel and al., where they show that only a few number of characteristics matters. They use a traditional they use a traditional Brandt model, which is in fact almost like our supervised portfolio, but with linearity and some. Yes, it's almost the same thing. In fact, almost that's the same idea. And what we decided to do is to create to expand their linear framework with our nonlinear framework, which is what we have presented in the interpretable supervised portfolio. So we follow Engel, and we have monthly rebalance portfolio of 100 large cap stocks. We only keep 100 large cap stocks because we have only monthly data, and we are well aware of the covariance estimation issues if we would have kept much more a higher number of stocks. Yes, we take transaction cost, predicted models, and here we chose two types of benchmark. So the regression models, which is very close to the Demiguel and Hall framework, the equal weight portfolio, and of course our nonlinear approach. So what we see is at a 1 month horizons, no one is able to beat the benchmark. At a 3 months horizons, we see that the direct approach with roll fit is equivalent to the benchmark, and at the 6 months horizons, roll fit with the direct approach is better than everything. The regression do not perform quite well, so that our first results. So again, non-linearity matters. What comes as a surprise is that the more homogeneous approach, so the direct minus 1/n, do not perform quite well. If I'm honest, I was not expecting this kind of results. I was expecting that homogeneous weight will be easier to forecast. I am trying to dig into this issue at the moment. I still do not know why this approach do not perform better. And as regard the cross-section of expected, the characteristics, we find that on 30 characteristics matters. So we don't need advance of characteristics, but we need to account interactions, because feature and feature interactions matters, and there is considerable time variation in feature importance that makes everything difficult. We have to look at the interaction between features and macroeconomy. In fact, that's what we are doing in the third paper that is available on SRCN, which is looking at interaction in asset pricing. And if we look at the top 10 characteristic, we have DIVO, which is the omission of dividend. SIN, is it a SIN stock? And DV, which is, I think, when you start to create to pay dividend. So it's a lot about dividend and SIN stocks. So if I want to conclude, as I don't have a lot of time left. So the interpretable supervised portfolio, it's an effective, interpretable, flexible, forward-looking, and nonlinear framework. We really like it in AXIM. We have that into production, and we are looking at their results on a daily basis. Looking forward, I would like to know if we change the traditional Markovitch approach by a clustering-based asset allocation. Do we manage to perform better or not? At the time, deepening the analysis of stock characteristics that we have done in the third paper, and look at bonds on a bond level, because we are close to AXA, which is insurance company, so that is really invested in bonds. So that's really what I wanted to show. So the main idea is really to you can have an interpretable nonlinear model that works quite well with the roll fit approach, And the supervised portfolio is an effective framework to allocate capital.
Thank you, Thomas. And so I would like to, I have some echo here, so I don't know, maybe somebody should mute. I would like to ask our reviewers for a show of hands, please, if they have questions. Use the raise hand feature in the menu if you have any questions. Michael Wolf is the first one up.
All right, thank you for the presentation. It's very interesting. I was still wondering, you are predicting optimal weights, but it's something you never know. So, I mean, what exactly do you put on the left-hand side?
I put weights, but in fact,
which weights?
Yes, that's I know it's a little bit tricky and quite confusing, but traditionally you put returns. You don't know the returns either that you put in your Y on the left side when you create a regression. You have returns.
I mean, no. The returns are observable, but the weights are
yes,
not.
The returns are observable. I agree. So what we do is we start by creating an optimization, knowing the returns and the risk. So in fact, we will say that given that in the next month, I don't know, Apple will perform well, Meta won't perform, the correlation will be quite high between the stocks. What would have been the weights that the allocator would have created? So we create a Markowitz with that. And in my example, it will have almost only Apple and a few Meta. And our weights, our forecast will be 0.9. I don't know if the optimizer say 90% of Apple and 10% of Meta. And what we try to forecast is 0.9 and 0.1, given the stock characteristics. But that's really tricky to show, and everyone is struggle with this idea. I have seen it, I've presented many times, and I have to change the way I present it because no one is understanding it. So I may give some example, more example. But okay. That's really what we wanted to.
Thank you.
Okay, thank you. Kaushik is the next one with a question.
Hey, thanks for the presentation. So it's a follow-up question. So if my understanding is correct, you actually construct the optimal weight first and then forecast. So in Markowitz optimization, we know that there are instabilities due to the covariance estimation. So if you're trying to forecast something that's already unstable, then won't you expect something unstable? So I was a bit puzzled by that actually.
In fact, I agree. It doesn't change anything on the issues with the Markowitz approach. It's unstable, it's concentrated, portfolio are not so stable. So that's why when in the first paper, we have found that in fact, the new approach is much more stable because the weights that we find do not change so quickly than the optimizer, because we know that when we have a Markowitz approach and if the optimizer can gain 0.1 in the returns, it will go all in on it. But with our approach, in fact, it's much more stable. That's what we like. But I agree that in practice, in production, we have worked a lot on making the target more stable, so with transaction cost, with limiting the turnover. But the main advantage is that we don't have forecast issues on expected returns, which are the most important part of instability for the optimization. So as we have the exact returns, we have more stable portfolios. In fact, we have a more stable target, and we work on transaction cost and so on to stabilize the target even further.
Okay, thank you, Thomas. Then I'd like to go on and ask Marcos to ask his question.
Thank you, Horst, and thank you, Thomas, for this presentation. I'll follow up on Michael's question. So you have a wide array of targets. Is this wide array multiple columns? Actually, are you trying to do a multi-target prediction?
Yes, that's a really good question. In fact, we have tried both, if we are honest. The multiple target prediction was harder to create and was not performing as well as a simple target. In fact, we decided to go to a panel approach, which is quite traditional, in fact, in the machine learning approach. That's what they are doing in Guillaume Hall. That's what Guillaume Coqueret and his co-author are doing in their book, Machine Learning for Asset Pricing. But if we want to use a multiple prediction with LightGBM at the time, now I think that there is a softmax model, but I'm not sure. At that time, it wasn't, so we created one, but it was difficult to explain, difficult. The panel approach is much simpler to estimate and much simpler to put into production.
Okay, now you are making these predictions on the weights. How do you ensure consistency of the predictions, meaning that when you computed the optimal weights, which you want to learn, there is a covariance structure and the constraints are applied to the calculation of the weights. But then the model needs to learn those weights. However, the constraints are no longer operating. They need to be learned. And also the correlations between the variables need to be learned as opposed to being applied in a portfolio optimization. So how do you ensure that these forecasts are consistent and are coherent between them?
Yes, that's a very good point, and one of the main issues of our approach. In fact, we do not. So we have a filter after that to make weights consistent. We didn't
Tell us about
find
that filter. That I didn't get the filter explanation in your presentation.
No,
like
we don't. We talk to in the paper. We just ensure that the sum of weights is still 1, and we stay within the constraints. In fact, so there is a second. I don't know how you call it. Yes.
So you apply multiple passes in order to renormalize the weights and push them into the boundaries.
Yes, but in fact, we were quite surprised because the weights almost stay in the boundaries. The model quite achieved to learn the boundaries. But sometimes you have some, I don't know if the constraint is 0.2, sometimes it goes to 0.22. So we have to make some small modification, but it's not so big. The sum of the weights is not always 1, for sure. So we normalize it almost every time.
Okay, thank you.
Yes.
Thank you. I think I would like to turn over to Enzo next with a question.
Hello, thank you. I think I have another question on the same line, and it's my intuition would be that in the absence of complicated constraints, the weights would just be maxed out on the largest return, real return, and the minimum one would be your minimum floor level at the minimum return. So what constraints and what covariance you put there is very important. Just saying that you're fitting on that stuff. You're fitting on the covariance and on the constraints. That would be my intuition. What do you think?
Yes, I agree. But that's the same thing when we do traditional optimizer. If we forecast the returns, and it will be very long on the most interesting returns, expected returns. Yes, we have to constrain everything before optimization in both approach, I think, with the traditional one and with when we create weights. That's what I would like to see. The performances when we do a hierarchical approach instead of traditional Markowitz, because it's much more diversified. We didn't in the paper. We didn't try with risk-based approach. We try it in AXIM, within AXIM, and in fact it works quite well too.
What covariance are you using?
In the risk-based approach,
in
fact, we are using the expected covariance.
Okay.
The one that we'll realize in the months to come, in fact.
Oh, and you're using the real. Oh,
yes,
interesting.
The real one.
So you take the next month of returns, you fit a covariance on that one, and you use that in the optimization.
Yes, and then we try to forget that. That's why, in fact, we allow to limit the uncertainty on returns and return covariance. It may be one of the reasons that why this framework works quite well.
So you are predicting the covariance structure as well. Very, very interesting.
Yes. Yes, we are.
Kaushik has a hand up for another question. Kaushik?
Oh, actually, I think I forgot to lower my hand. Sorry.
Oh. Okay, no problem. Alexander next.
Yes. Thank you for the presentation. How stable are the functions which you learn if you move a little bit the learning period, and as far as interpretable, you can control this function, the coefficients. How stable they are?
That's a good question. In fact, if we go too far away from if the investment horizon is too long, I don't know, 6 months, 9 months, and you have a big drawdowns, I don't know, in the last part of your forecasting horizons, I don't know, in the last 2 or 3 months. So the weights will be quite negative for your allocation, but it will be too soon. In fact, you will have reasons, but you will have reasons too soon. So you can take too long horizons, or you have to tackle the fact that at the end, if you have a drawdown at the end of your horizons, it creates problem in the applications.
Okay. Another just question. Imagine your evolution, your asset returns. Imagine the evolution. You can model it as a certain function of your features, right? So say, yes, this feature will be VIX, right? So this will be the volatility of of our returns. In this case, you can do these Monte Carlo simulations in order to see how your method can be compared with the optimal, which more or less, because the model. Did you do experiments like this?
No, we don't thought about it. Yes,
when you know the model, very simple. Just then you can potentially come up with the weights calculated using the Markovits, for example, where these features are calculated as of today, right? And then you can compare, and then you compare your technique by each Monte Carlo simulation. Yeah, can be just an idea.
Yes, I not. I didn't. We didn't thought about it.
Thank you.
Okay, then I'd like to ask George to come forward with his question.
Thank you. Yes, thank you very much. Thank you, Thomas, for this very interesting talk. This is a very interesting subject. My question is actually a little bit of a follow-up of the two previous questions by Dr. Antonov and Dr. Kushik. So, you mentioned stability, and can you please clarify or define more precisely what type of stability you analyze? Because you seem to implicate that you are finding stability on the weights, but ultimately what you really care about is the stability of the return and how good your return is. So what kind of measures of stability you are using? Of course, I understand. Yeah, please.
Well, we are just using the evolution of weights given transaction cost. So as transaction costs are quite high, the more you move, the more you pay. So we really try to limit transaction cost. That's really what we look at for stability. We don't look at the stability of returns for sure, and what we found is more stable model perform quite better in comparisons with more volatile one. But no, the measure of stability was the evolution of weights.
Okay, all right. Yeah, also the follow-up, I think that the idea of having that this was Dr. Antonov's suggestion of having some model that's not too simple, but you know already the solution and see how it performs would be a very interesting thing, because it would be allowing you to really assess your stability and your effectiveness of the solution. No?
Yes. We did not look at model stability. We look at weight stability, but yes, we should look at that too.
Okay. Thank you very much. Appreciate it.
Thank you.
Okay, I don't see any more hands up. Mark Wolf has another question. Yes, please go ahead, Mark.
Okay, I do have a final one. It's not in the talk, but in the paper. I mean, to me, maybe the main result is Exhibit 6, where you compare various strategies, say, to 1/n in terms of, different metrics like the Sharpe ratio and so on.
Mm-hmm.
But I mean, it seems not a big outperformance, like kind of close to 1/n. Isn't that a bit disappointing?
In fact, given our framework where we have only the biggest stocks and only 100 stocks, I'm not surprised. It's quite difficult to beat the benchmark.
I have to disagree. I mean, beating 1/n with 100 stocks should not be that hard.
Really?
Yes.
So no, it was in line with what we were expecting. So not so big over performances. Okay. But statistically, sorry, it was better. That's what we really look at, because over performance, when we don't have the right transaction cost and the one that we would have used in practice, it's difficult. Historical over performances. What we want to look at is a concrete one with our own transaction cost that we won't reveal for sure because we are not able to. But what we really wanted, that's the MCS and to focus on statistical performances.
Okay, thank you.
Okay, any more questions? Then I will make a last call for hands being raised. If not, then I'd like to thank Thomas and his colleagues for presenting, and of course all the reviewers for joining for the third paper. And then I look for you all will be back in about an hour for the last paper. So thank you for doing this. And I'd like to thank especially Massimo, who will chair the last paper presentation in about an hour. With that, farewell and have a good afternoon or good evening. And I will turn off, just to tell you this, I will turn off the recording now.
Thank you, everyone. Thank you.
Bye-bye. Thank you.
Bye-bye.